Hi all, I am Agastya. I am a second year undergraduate at CMI. My background is in math and I am interested in AI. The key direction of AI that I'm interested in is AI alignment, and I am working towards that in general. These evening sessions are for my coding improvement, which I'm not very good at. Uh, I will be doing this about every day. So let's get right on. Yesterday we did uniform vectorization and we simulated the game of life. Today we will start with temporal vectorization. Okay, so this by the way. So yesterday we did the Q-learning paper. This talks about how Q-learning is just Dijkstra's algorithm in disguise. We will cover this probably tomorrow. We'll see. But for today, we are going to continue with Numpy. Alright. So for NumPy, the goal is to do this, by the way, from Python to NumPy, the entire thing. We are currently at temporal vectorization. This is my NumPy improvement code for that. There is also 100 NumPy exercises that we are going to look at later. Okay, great. Let's start. Okay, so this is the defining a Mandelbrot set where you apply the same function repeatedly and the sequence that you get, it converges at z equals 0. That's right. Okay, so my bad. It does not converge. It says it does not diverge, right? That does not mean that it needs to converge. It simply says, you know, it can be in like the range, say -1 to 1 or so on and so forth. I think that is what they mean by divergence here. So just writing some notes, it's fine. Okay. Actually, I'm not really sure about this. Do they mean it mathematically or not? Because in mathematics, when we say does not diverge, it certainly means it converges. So let us check it out. Mandelbrot set. So it's all about staying bounded or escaping to infinity. It does not say convergence. So it's not really a mathematical term to use, I guess. Bounded would be a better term to say. Does not diverge to infinity. Yeah. It's not really a mathematical guide, is it? Category line. Sure. So it's c square plus c. And you do it for a fixed number of iterations, I guess. X and Y maxital and horizontal. Okay. What a, it's not a great guide, honestly. What does it even mean? Okay, so let's run it through this. Hopefully this explains it better. Okay, so they are claiming here that the repeated application of the function itself is what is hard to vectorize. Okay, so that is what our horizon is. It says if the absolute value of my complex number becomes greater than this horizon, this modulus, then we return the value, the index at which it does so, and we say it diverges. Otherwise, we just compute the function. Okay. Great, and then it says okay, we iterated it this many times, and then you have R1. What is R create? What is R for? I times. Okay, so x max and x min are fixed values, including xn and yn, in which we are calculating the range. Okay. So we have the standard Mandelbrot function, and then we are computing it for each complex number in a certain range, and then we can finally visualize it, and we'll see a fractal of this sort. And this is exactly what we are going to implement in Numpy through vectorization. Okay, great. Although this requires some sort of detailed explanation of. Okay, just a second. All good. So did they even explain what temporal vectorization is? They have not yet explained it. Whatever. Sure, we do this. This part is exactly what we discussed, and we do this for a certain number of pixels in a range, right? Which is what they needed to explain properly. I meant trust, but okay, whatever. Okay, so they're using advanced indexing in Numpy with the less. Okay, synonymous terms. We are good there. Okay, great. This makes more sense. So this is how you're creating your pixel table. X-min is the left edge of your screen and X-max is the right edge. Okay? So this obviously increases, this determines the length divided by the number of points that you're going to be using. So that's the length of each pixel that you have. And you iterate over I and you start with your X-min, which is where you're starting. It may as well be the origin by translation, right? And then you iterate over I to do that. Let's see, they must have iterated over I. That's right, as we assumed. And they're doing the same thing in the y-axis. And then they are calculating the Mandelbrot for each complex number in this range. Great, great. Yeah, beautiful. Wonderful, wonderful. So now let's move on to the Numpy implementation. Yeah, seems we're like we're faster today. Okay. Even though I did import it before, I'm going to do it again. Import Numpy as NP. Alright. Definition Mandelbrot Numpy. Uh, we are going to assign it to a point. Okay, good. X min, that is the left coordinate. So we must have X max, Y min, Y max. That would be the range. Xn, which is the number of points that we are going to be using. Okay, Yn, maxiter, number of iterations that you are going to be using. And then we've got our modulus that we need to check with. They're calling it the horizon. Great. We'll call it the same. Horizon equals 2.0. Look at how simpler the implementation simply becomes. X1, X max, Xn. D type equals NP dot. Float 32. Great. They're going to be using this. And then we are going to do the same thing for Y, by the way. Do not need the help of the AI here. What is this, the cursor? It's probably not it. Yn, Y max, so Yn D type equals NP dot float 32. Once we have this, what are they doing? Okay, what is this? Interesting. Is this a complex number? And then they do the multiplication with 1j. What does this mean? Oh, wish they explained that code. Great, sure. What? Okay. So they're using the following convention here. You want to say that Y is a list. So to do that, you put the comma and the none here. Oh, interesting. So this is how you're making it a column vector. What the? And finally use broadcasting. This is how they are creating the complex plane. Okay, okay. Let us try to play with Gemini here. Let's see what it says. I, I don't really want. I thought they are the same thing. So I'll just ask if what it means. Oh, interesting. So it adds a new axis. Sure. So Y was already a 1D array. And now we have added a new axis to it. But there were also three elements, right? And now it's one axis. I see, I see. So it simply creates a 3 cross 1. Now you have obviously embedded your list of numbers into a vector space. And very interestingly enough, for some reason, it seems that I is actually donated by J instead of I. Great. And broadcasting is just beautiful, let's just say that. So it says we have got a what 1 cross 2 and we've got a 2 cross 1. So it says how do I add them up? I cannot. So I just make them the same shape, and what do? Well, instead of, that's how broadcasting works, it just copies it intelligently and then it adds them up. Very nice, very nice. Okay, so let me just write down what the syntax mean. Syntax needs some explanation for C. Actually, no. I'll write this here. So suppose I have two arrays. X and Y. Here is what the following code does. Okay, all good. C equals, what did they do? X plus Y, we need to say, great, times 1j. Yeah, that should work. Okay. The does the following. Says is an alias for creating a new access to an array. It can easily be generalized to creating a new access on a tensor. So how would we do that? You'll just say colon, whatever I think it's called, colon, comma, none. That would create a 2D matrix, transform a 2D matrix into a 3D matrix. That is what the none is for. What about 1G? It acts as the imaginary number. Wait, what if I just multiply it by j? Will it understand that? Let's see. Yes, it is not I. Finally, the addition is done through broadcasting. What it does it do? It creates copies to make them the same shape and then it adds them up. Great. Shouldn't it be 1 plus 10j, 1 plus 20j? Should my grade not be... Wait, is that what we get by the way? Oh fine, sorry, my bad. They do get all the 4 different elements. I thought they were the same, that's why I was confused. So let's see what they do. 1 2 1 2. Oh, and then it adds element wise, right? So of course it will be like that. Makes them the same shape through copying and then adds element wise. Syntax question. Instead of multiplying by 1j, could I have just multiplied multiplied by j. Okay, great. Let's move on. And now you say n equals np dot zeros. I want c dot shape and I want d type equals np dot float 32. Great. Is that what we want? D type is equal to n. Cool. Okay, I guess what this is that we are initializing a matrix such that for each coordinate we are going to assign an integer value. That is, it is either going to be max iter, that integer value, if it does not diverge in that given range, or it's going to be the integer at which it did pass the horizon. So that is what I suppose n is. And let us check out z, whatever. So z equals np dot zeros, if that is what they still want. Oh, by the way, it seems there is no e here, my bad. I suppose they also don't want a shape. And what would they want? D type equals np dot complex 64. What is this for? What could this be for? This is what your initial integers become. They're all 0, right? And now we are applying the transformation each time. It's z square plus c. Well, not this matrix C, but the element number C. This is what they have described as Ci. Wait, is it? Let me just confirm. We cannot just do that. Sure. Ah, right. That makes sense. That makes a lot of sense. So now while it explains that, please wait a minute, I'll just get my laptop charger. Okay, we're back. Sure, that's what I thought. That's why you're initially using it with complex numbers and it's all zeros. Start it with zeros, right? Answer B. How do we add with C? It is certainly not the matrix C, right? Because yeah. Why are we? What the? Whoa. I had missed this here. I need to find C to be Z. Ah. Oh. Oh, I see. Okay. My bad. That was a logical error. Quite a foolish one. Yeah, okay, cool. One needs to read this carefully, right? So that is why you're making C as the grid. Cool. Grid of complex numbers to check. Maxiter or the integer will be across the horizon. Evolution of FC as we evolve. From Z equals 0. Great. So now we have this. For n in range maxiter, you try it for all of them. Z becomes Z times Z plus C. Same matrix shape, no worries. Right? Okay, here's where they're using Numpy now. Okay, they're doing this before. Absolute Z is, I believe, wow. Horizon. This is why Numpy is so nice. So you just do absolute Z and it just calculates the absolute value of every integer, every cell in the grid. I believe this will be a Boolean matrix. And now we do that. Ni is equal to n. What does that mean? Okay. So this I understand. What you're saying is that, if it has crossed the limiter, why should I compute for that value. I'm going to be efficient and I'm only going to compute it for those values for which this evaluates to true. Okay, I suppose there's also what it means. Crazy syntax. Crazy syntax. Great. N equals matrix. Alright, great. Makes sense. Oh yeah, this is not the best thing to do. Wow, crazy. Okay, you wanna call it that, you call it that, whatever. Same initialization they do? No, oh, they have now changed the initialization. So this is what it's like. What does np.mgrad even do? Here's to hoping everything's going well. Great. What's all this? Okay, great. We're going to learn 4 different number concepts advanced. Here's the ID cards. Okay, great. Okay, mgrid stands for some more syntax. Code np dot mesh grid. Yeah, this seems fine. This is the most interesting thing to me, honestly. Just a minute. चलेगा भी आधी घंटे और चलेगा आधी घंटे और चलेगा. Okay, so the first tool is np.meshgrid. It will create two matrices for us. Alright, so it creates a row matrix as well as a column matrix. So if we have a 3 by 3 grid, so it ranges from 0, 0 to 2, 2. We make two copies of it. So in the first copy, we are counting the number of rows. So the top row is say 0, 0, 0. Oh, right. See, that's what it is doing. It's not actually counting the x coordinate and y coordinate respectively. It is instead counting the number of rows and number of columns instead and indexing that. So the first row is 0, 0, 0, 1, 1, 1 and 2, 2, 2. And for the columns, it'd be the 0th column, first column and second column. And so this is how we would implement it. To repeat, we have got a Cartesian system in which we are going from 0 to xn and 0 to yn. And we create two copies of the matrix that forms out of our Cartesian system. In the first matrix, we ask which row are you situated in from top to bottom. So the first row is 0 and then 1 and all the entries and so on. And we do the same thing for the other matrix where we're doing it column wise instead, left to right. Great, so now we can move on from this. So let us write that here. Xi, yi equals np dot m grid, which I believe is what the syntax is, 0 xn, 0 yn. And now you obviously, in these two matrices that we have situated, we want to uniformly put numbers there to represent the coordinates that we have. Okay, first of all, what they're saying is, we want all of them to be of a certain type as type, which is explicit typecasting, np dot uint 32. So what does uint mean? Let's see that. Okay, my bad. That's going to be xi here. So this is, yeah, that's what typecasting it is. You're creating a map. What is uint 32? Great. This is not needed for today. Now you do the following. X equals np dot len space. Okay, so what are we doing? Okay, unsigned integer. Interesting. Sure, it will be unsigned because when we do z squared plus c starting from 0, z squared is anyways greater than equal to 0, and c, because I suppose our coordinates are going to be greater than equal to 0. Okay, here we are using fancy indexing. Sure. Sure, it will do that. Wow, this is absolutely beautiful. So for any number in xi, we say what is this number? Say it is 10. We create a map so that we retrieve the 10th element of our length space array, and we map that 10 to the value of that corresponding integer array itself. Nice. So xmin, xmax, xn, xi. Is that right? That's right. And you say d type is equal to np dot. Sure. D type equals np dot float 32. Y equals np dot space ymin, ymax, yn, d type float 32. Wow, lot of mosquitoes today. I am going to wish to end it early as fast as possible. Yeah, and you do the standard thing, right? Just go with np dot zeros. So what is this for? Let's see. Now this. Oh, now they're going to explain why it is better. Yeah, that's right. X holds the real coordinate and y holds the imaginary coordinate. Great. Now explain the n. Let's see. C dot shape d type equals int np dot int 32 z score. So what I've been noticing is that, okay, let me just do this first. Complex 64. That's right. So what I've been noticing is that, you see, the Numpy arrays are quite similar to your C++ arrays, which is sort of, superficially speaking, what gives them power. We have already discussed why they are faster through the strides concept, but we see some sort of similarity between the Numpy array and the C++ array, but it is not exactly similar. Let us remember that in the C type array, you have to first declare the data type of a variable, but we are not doing that here. And Python does that on its own intelligently. And I'm sure it's homogeneous in the Numpy arrays as well. But you may not need a broader category when you can work with a shorter category. So I think that is why it is important to put this d type, to initialize or to declare your d type based on what the context is, making your code truly optimized. Sure. So I'll just write permanent thing to be remembered. So even though we are optimizing our code, so we do this, and then we declare the shapes of all our matrices to be the same. Let's see what this means. So clearly these two things are okay. So this says uh, at what at what index did your thing diverge from the horizon, if it even did, and you need that memory for every coordinate in your system. And this says what was its value when it whatever. Yeah. This is something that now we need to understand. Why would you do this? Okay, yeah, they explain this now. Oh wait, what? Clearly these are all matrices. None of them have been flattened out yet. So once we have done this, we are obviously going to do what we did in the weaker Numpy implementation. So we are going to initialize it with zeros, np dot zeros. Same shape will be for so we are going to initialize for each coordinate in our system to 0, and of course the type will be a complex number with 64 bits. So we say Ryan range filter max. Now this is exactly where the new engineering will help us optimize the code further. Okay, so that is what I will do. So the Boolean indexing that we do, it flattens our matrix into a 1D list. Oh right. So we are flattening it at the very start before we start our looping. And this is exactly what is going to help us optimize our code. Okay, I see. So, okay, so Lenzy calculates the number of pixels that are non-zero. Sure, if the Mandelbrot set is indeed non-empty, then it will not break. But it's a safe spot to put this here. And now it's all just syntax. So that's recording and okay, I see. So this is how np.multiply works. It takes three arguments. What is the matrix that you're going to create, and what are the two matrices you're going to multiply, and we put it to the same matrix so as to not waste memory and keep the code efficient. And then you say, okay, I'm going to add z to c, and I'm going to keep this memory to z itself. Great. Okay, sure, fine. Boolean list. And now we want to remove them because we do not want to make calculations for things that are already dead. And since we've already flattened it out, it's quite easy to do so. But you also need it tagged to the coordinate index that they're at. Great. This is Python indexing at its best. So you see, we've already created these. This is why we created x and y. So to store the coordinates, and we are going to initialize this to this. What do you do with z, by the way? xi, I, yi, I. So you're going to update it and then do it? That's right, we are. Great, we have successfully updated.
Thank you, sir.
Okay.
जो भी यहाँ पड़ा है ये अशुभ है, ये ओनर का है जो हमने अभी शुरुआत में नाम से शुरू वाले हैं वापस। नहीं गंदा है भाई, इसको नाम से कभी नहीं करते। अभी सिम पे हाई वो सेट पे रखना है, इतनी बचा है।
And then you simply delete all of them. Peak. what is T here? God. And this should work. Where the oh my god. Okay. Oh my god. Tell me, no, there is no way to do it. Lol. Great. We have successfully identified our Mandelbrot set. Fine, you just did that. Remember that it was actually sort of flipped, which is what the initial doubt was, so we need to flip that back. The dot T is for the transpose. So we are going to document all the syntax that we have just learned. Okay, so we have already explained the mp.grid. Now linspace is something that we understand. Simple syntax, but we will document this nonetheless. Multiply the second and the third element and store the memory into the first element. Address. Y equals condition Z is a Boolean list. np dot negative I is a not operation to each of the element in the list. Great, everything else is understood anyways. Okay, so let's run the visualization code now. Let's understand the error. Let us write the plotting. And for a 1000 x 1000 pixel system, the Mandelbrot set has been finished in 0.6 seconds. And look at this beautiful visualization. So the black part represents the C values for which the iterated application of the function did not diverge, and this results in a fractal like system. And for the y-axis, the y-axis is just the imaginary axis. The darkness of the color red indicates at which iteration it died off. For those that did not die off, well, that's just 0. And so we're done. Let's meet tomorrow evening. This will be the thumbnail that will be put. Okay, great. I will end the session here today.